Hello everyone, I am Abinaya RVE from AIDS first year B section. I am here to explain about the DSD laboratory experiments from 1 to 8. So let's see the 1 to 8 experiments. The first experiment is the study of logic gates. The second experiment is the study of adders and subtractors. The third experiment is design and implementation of code converters 1. The fourth experiment is design and implementation of code converters 2. The fifth experiment is design and implementation of parity generator. The sixth experiment is design and implementation of multiplexer and demultiplexer. The seventh experiment is study and implementation of encoders and decoders. And finally, the last experiment is study of flip-flops. The first experiment is study of logic gates. The aim of this experiment is to study about logic gates and verify their truth tables. The first logic gate is an AND gate. So for that, we are going to add two switches and logic gate and a light bulb. We are naming the first input as A and the second input as B. The output is named as AB. Now we are connecting A and B with the AND gate and the output AB with the wire. We are also adding a truth table. So when the inputs are 0, 0, the output is 0. When the inputs are 0, 1, the output is 0. When the inputs are 1, 0, the output is 0. When the inputs are 1, 1, the output is 1. So this is all about AND gate. The next gate that we are going to study is an OR gate. For that we are going to add two switches, an OR gate and a light bulb. The first input is named as A and the second input as B. The output is named as AB. We are connecting A and B with the OR gate and the output AB with the light bulb. We are also adding a truth table. So when the inputs are 0, 0, the output is 0. When the inputs are 0, 1, the output is 1. When the inputs are 1, 0, the output is 1. And when the inputs are 1, 1, the output is 1. So this is all about OR gate. The next gate that we are going to study is a NOT gate. For that we are going to use a single switch, a NOT gate and a light bulb. The switch is named as A and output is named as A dash. We are placing the truth table here. A is connected with the NOT gate and output A dash with the light bulb. So when the input is 0, the output is 1. When the input is 1, the output is 0. So this is all about NOT gate. The next gate is an XOR gate. For that we are going to add two switches, an XOR gate and a light bulb. The first input is named as A and the second input as B. The output is named as AB. Now AB is connected with the XOR gate and output AB with the light bulb. Here we are adding a truth table. So when the inputs are 0, 0, the output is 0. When the inputs are 0, 1, the output is 1. When the inputs are 1, 0, the output is 1. And when the inputs are 1, 1, the output is 0. So this is all about XOR gate. The next gate that we are going to study is a NAND gate. For that we are going to add two switches, a NAND gate and a light bulb. We are naming the first input as A and second input as B. The output is named as AB. Now A and B is connected to NAND gate and the output AB to the light bulb. Here we are placing the truth table. So when the inputs are 0, 0, the output is 1. When the inputs are 0, 1, the output is 1. When the inputs are 1, 0, the output is 1. And when the inputs are 1, 1, the output is 0. So this is all about NAND gate. Next we are going to study about a 3-input NAND gate. For that we are going to place a NAND gate and increase the input count to 3. Next we are going to place 3 switches and a light bulb. The first input is named as A. The second input as B. And the third input as C. The output is named as A.B.C. First, the connections are given from the switches to the logic gate and the output wire to the light bulb. The truth table is displayed here. So first, when the inputs are 0, 0, 0, the output is 1. When the inputs are 0, 0, 1, the output is 1. When the inputs are 0, 1, 0, the output is 1. When the inputs are 0, 1, 1, the output is 1. When the inputs are 1, 0, 0, the output is 1. When the inputs are 1, 0, 1, the output is 1. When the inputs are 1, 1, 0, the output is 1. And when the inputs are 1, 1, 1, the output is 0. So this is all about 3-input NAND gate. Next gate that we are going to study is an OR gate. For that we are going to add two switches, an OR gate and a light bulb. The first switch is named as A. And the second switch is B. The output is named as AB. We are connecting A and B with the NOR gate and the output AB with the light bulb. We are placing the truth table. So when the inputs are 0, 0, the output is 1. When the inputs are 0, 1, the output is 0. When the inputs are 1, 0, the output is 0. When the inputs are 1, 1, the output is 0. So this is all about NOR gate. The second experiment is study of adders and subtractors. The aim of this experiment is to construct the adders and subtractors and verify its truth tables. So first we are going to construct an adder. For that we need two switches, an XOR gate, an NAND gate and two light bulbs. The first switch is named as A and the second switch is B. The XOR gate acts as the sum and the AND gate acts as the carry. We are placing the truth table here. The switches are connected to the logic gates. And the output wire to the light bulbs. So when the inputs are 0, 0, the outputs are 0, 0. When the inputs are 0, 1, the output is 1, 0. When the inputs are 1, 1, the outputs are 0, 1. When the inputs are 1, 0, the outputs are 1, 0. So this is all about half adder. So next we are going to construct a full adder. For that we need 3 switches. 2 XOR gates, 2 AND gates, and an OR gate. You also need 2 light bulbs. The first switch is named as A. The second switch is B. And the third switch is C. The XOR gate acts as the sum, and the AND gates acts as the carry. The connections are given from the switch to the logic gates. And the truth table is placed here. So when the inputs are 0, 0, 0, the outputs are 0, 0. When the inputs are 0, 0, 1, the output is 1, 0. When the inputs are 0, 1, 0, the outputs are 1, 0. When the inputs are 0, 1, 1, the outputs are 0, 1. And the inputs are 1, 0, 0. The outputs are 1, 0. When the inputs are 1, 0, 1, the outputs are 0, 1. When the inputs are 1, 1, 0, the outputs are 0, 1. And when the inputs are 0, 1, 1, 1, the outputs are 1, 1. So this is all about full adder. So next we are going to construct an ARP subtractor. For this we need 2 switches, an XOR gate, an AND gate, and an OR gate. We also need 2 light bulbs. Here the first switch is named as A, and the second switch is B. This acts as the difference. And this acts as the borrow. And the truth table is also displayed here. First, the connections are given from the switches to the logic gates. And next, the output wires to the light bulbs. So when the inputs are 0, 0, the outputs are 0, 0. When the inputs are 0, 1, the outputs are 1, 1. When the inputs are 1, 1, the outputs are 0, 0. And when the inputs are 1, 0, the outputs are 1, 0. So this is all about half subtractor. Next we are going to construct a full subtractor. For that we need 3 switches, 2 XOR gates, AND gates, 2 NOT gates, and a single OR gate. And we also need 2 light bulbs. The first switch is named as A. The second switch is B. And the third switch is C. This acts as the difference. And this acts as the borrow. First, connections are given from the switches to the logic gates. And the output wires are given to the light bulbs. Now the truth table is placed here. So when the inputs are 0, 0, 0, the outputs are 0, 0. When the inputs are 0, 0, 1, the outputs are 1, 1. When the inputs are 0, 1, 0, the outputs are 1, 1. When the inputs are 0, 1, 1, the outputs are 0, 1. When the inputs are 1, 0, 0, the outputs are 1, 0. When the inputs are 1, 1, 0, 1, 0, 1, the outputs are 0, 0. When the inputs are 1, 1, 0, the outputs are 0, 0. And when the inputs are 1, 1, 1, the outputs are 1, 1. So this is all about full subtractor. The third experiment is to design an implementation of code converter 1. The aim of this experiment is to design and implement 4-bit binary to gray code converter and gray to binary code converter. First we are going to do binary to gray code converter. For this we need 4 switch, 3 XOR gates, and 4 light bulbs. First we are going to give switch to logic gates connection. And the output wires to the light bulbs. So this is the binary to gray code converter. So the next is a gray to binary code converter. For this we need 4 switches, 3 XOR gates, and 4 light bulbs. Now we are going to switch to logic gate connection. and the output wire to the light bulbs. So this is the gray to binary code converter. The fourth experiment is to design an implementation of code converter 2. The aim of this experiment is to design and implement 4-bit BCD to XS tree code converter and XS tree code to BCD code converter. So first we are going to do BCD to XS tree code converter. For this we need 4 switches, 3 NOT gates, 4 AND gates, and 4 OR gates. We also need 4 light bulbs. So now we are going to give the connections. So this is the BCD to XS tree code converter. Next we are going to design an XS 3-bit code to BCD code converter. For that we need 4 switches, 2 NOT gates, 2 AND gates, 2 OR gates, two XOR gates, and 4 light bulbs. So now we are going to give the connections. So this is the XS3 to BCD code converter. The fifth experiment is to design an implementation of parity generator. The aim of this experiment is to design and verify combinational logical circuits of a 3-bit parity generator and jugs. For this experiment we need 3 switches, 2 XOR gates and a single NOT gate with 2 light bulbs. The connections are given as follows. So this is the parity generator. The sixth experiment is to design an implementation of multiplexer and demultiplexer. The aim of this experiment is to design and implement multiplexer and demultiplexer using logic gates and study of IC 74150 and IC 74154. Now we are going to design a multiplexer. For this we need 6 switches, 2 NOT gates, 4 AND gates, 'With the input count 4, and an OR gate with input count 4. The connections are given as follows. So this is the multiplexer. Next we are going to design a demultiplexer. For that we need 3 switches, 2 NOT gates, 4 AND gates, with the input count 3, and 4 light bulbs. The connections are given as follows. So this is the demultiplexer. Event experiment is design and implementation of encoders and decoders. So first we are going to do an encoder. For this we need 7 switches, 3 4 input OR gates and 3 light bulbs. First we are giving the connections from the switches to the OR gates. For the first OR gate we are giving the connections from the switch numbers 1, 3, 5 and 7. For the second OR gate, we are giving the connections from 2, 3, 5 and 7. And for the last OR gate, we are giving the connections from 4, 5, 6 and 7. Next, we are giving the connections from the OR gates to the light bulbs. So when y1 is y1, the output is 0, 0, 1, and y2 is 1, the output is 0, 1, 0, and y3 is 1, the output is 0, 1, 1, and y4 is 1, the output is 1, 0, 0, and y5 is 1, the output is 1, 0, 1, and y6 is 1, the output is 1, 1, 0, and when y7 is 1, the output is 1, 1, 1. This is all about encoders. Next we are going to see about decoders. For this we need 2 switches, 2 NOT gates, 4 AND gates and 4 light bulbs. First we are giving the connections from the switches to the NOT gate and from the NOT gate to the AND gate. And then from the AND gate to the light bulbs. So when the inputs are 0, 0, the outputs are 1, 0, 0, 0. When the inputs are 0, 1, the output is 0, 1, 0, 0. When the inputs are 1, 0, the output is 0, 0, 1, 0. And when the inputs are 1, 1, the outputs are 0, 0, 0, 1. This is all about decoders. We are going to the 8th experiment, the study of flip-flops. The first flip-flop is SR flip-flop. For this we need 2 switches, 1 clock bulbs, 2 NAND gates, another 2 NAND gates and 2 light bulbs. First we are giving the connections from the switches and clock bulbs to the NAND gate and from the NAND gate to the light bulb. When the inputs are 0, 0, the outputs are 0, 0. When the inputs are 0, 1, the outputs are 0, 1. When the inputs are 1, 0, the outputs are 1, 0. And when the inputs are 1, 1, the outputs are 1, 1. This is all about SR flip-flop. Next is the D flip-flop. For this we need a single switch, 1 clock bulbs, 1 NOT gate, 4 NAND gates and 2 light bulbs. First we are giving the connections from the switch to the NOT gate and NAND gate, and then from the clock bulbs to the NAND gates, and then from the NAND gates to the light bulbs. So when the input is 0, the output is 1, 0. When the input is 1, the outputs are 1, 0. This is all about D flip-flop. Next we are going to study about JK flip-flop. For this we need 2 switches, a single clock pulse, 4 NAND gates and 2 light bulbs. In this, 2 of the NAND gates are 3 input NAND gates. First we are giving the connections from the switches to the NAND gates and then from the NAND gates to the light bulbs. This is the logic diagram of a JK flip-flop.